see how well that works.
Maybe I can go to state even
Are there any questions?
where is state? That's my question.
He didn't want to be in the same room with you. Oh, sure, that's it. Or me, he's insulting one of us. All right. So, going back to, I did the whole bit on Radians and Babylonians, right? Okay.
Sure, I think so. I don't know.
All right, speed, the math definition.
Distance over time.
So if I have something that's traveling in circular motion, what is the distance?
2 pi.
Or
Yeah. So 2 pi r over t. Actually, if I'm talking about going around the circle once, in which case the distance is 2 pi r, then the period is t, which is just 2 pi over t times r. This right here would be the angle that it travels through over time, which we talked about last time, is angular speed. Last time being on Friday. So the symbol used for angular speed is omega, lowercase omega. Matter of fact, a lot of the rotational slash angular stuff they use Greek letters for. So not a W. So V is equal to omega R. So if I look at centripetal acceleration, the magnitude is V squared over R. Well, V is equal to omega times R squared over R. I get omega squared R squared over R, which is just omega squared R. So if I have something traveling in circular motion, I know F equals ma. The centripetal force is mass times centripetal acceleration. We'll assume that they're in the same direction, in which case I have m v squared over r or m omega squared r. And this is the one that is more convenient when doing that lab. All right, questions to hear before I explain why this is more convenient? So we had that mass that was swinging around. There was the tube here. This distance here was L. So let's run through the process. What are the forces acting on the mass when it is on the far right or far left?
wait.
Anything else? All right, so this is force diagram. What is the direction of acceleration?
The center, north center.
In which direction is the center?
Right.
Okay. So my acceleration is that way. You're not in here.
No, I've got something to put in the cabinet and I'm right out.
Okay. So coordinate system, or coordinate axes. How would you set up the coordinate system? Running through the facades method, that's what you're doing. What do you want to make the positive directions?
Opposites are right.
Okay. Someone brave enough to make, to go for that. All right, so decomposition, do we need to break either of these up?
Yes.
Okay, what do we need to break up?
Tension.
All right, so so if that angle here is theta, then this angle here is also theta. So, I have weight acting down. One of these is going to be tension cosine, one's going to be tension sine. Which one's the cosine?
Yeah.
And how'd you get that?
Sine is on the vertical side.
Did I ask? I might have. The question in my head was not the question that I heard you answer. Which one is cosine, which one's sine?
Sine is going up.
Okay. Yeah. I was thinking I'd ask which one's cosine. So ft sine theta, ft cosine theta. Let's see, that was decomposition equations. How many equations of motion will there be?
3.
How do you get 3?
You have the sine, or the I. The tension, J hat, I hat, and then the weight is down. Oh, there's 3.
Is the weight in the parallel or anti-parallel to I hat or J hat?
Parallel to J hat.
Okay, so it's not a separate equation.
No.
So we'll have an I hat equation and a J hat equation. The J hat equation will have 2 forces in it. But it's just 2. All right, so as we do our equations of motion, we'll have the I hat and the J hat. So somebody give me one of them.
I hat is ft cosine is equal to mass times acceleration.
Okay. And it's centripetal acceleration, so I threw the extra c in there. That was the I hat. Put that in the wrong spot. All right, what's the J hat equation?
The ft sine theta minus weight is mass times 0.
All right. Now, we sort of went through this before. So if I'm looking at this one right here, I have tension cosine of theta is equal to m, and we have 2 different formulas for centripetal acceleration. There's the v squared over r, and there's omega squared r. So if I do m v squared over r, and then over here I'll write ft cosine theta is equal to m omega squared r. Now r is the radius of the circle through which it's traveling. Where is R in my green diagram over there?
This circle. Half of the circle.
Half of the circle? I mean, along the perimeter here, or circumference?
No, inside the circle.
Yes. All right, so that. All right, so that is R. And what's the relationship between R and L?
Tangent equals, or tangent of L over R. Tangent of theta is equal to L over.
No.
I mean, wait, no, what am I talking about? Cosine of theta is equal to L over R. I mean,
Closer.
R over L.
There we go. Adjacent over the hypotenuse. In other words, R is L cosine theta. So in this equation, we end up with tension times the cosine of theta is equal to mv squared over L cosine theta. And here, we have tension cosine theta is equal to m omega squared L cosine theta. These are both correct. But at least in this, I hope you can see the simplification we can do very quickly here. And so we are now dealing with things for tension. I know tension was the weight of what was hanging. Mass is what you're trying to find. Omega squared, we found by, well, you timed how long it would take to go around 20 times. Divide by 20, you have the time it takes to go around once. And omega is just going to be 2 pi divided by that amount of time. So that's why in this particular lab we did omega squared, m omega squared, instead of v squared over r. I spoke there why we did omega squared r instead of v squared over r. Questions? All right, let's continue on our fun-filled round of centrifugal motion. We gotta do the bank track problem, or at least one.
NASCAR.
If you wish, except I can try to remember the angle of the bank tracks. It's smaller than I thought it was. They actually like 25-degree angles. Let's make it a 25-degree angle. Although I was watching one show that talked about, there was a track in Germany where at the top it was like 70-degree angle. This is a rear view. All right, so we have a car that's going around a banked curve. Overhead view. It's going in that direction. That's the direction of the velocity at that moment. So what I want to know is if we're dealing with a frictionless surface, how fast does the car need to go in order to be able to make it around that curve without sliding up the ramp or down the ramp? Well, in order for that to happen, there must be some centripetal force. There must be something pulling it towards the inside, and in fact, we have that. So let's start out with, as we've always started out, with the force diagram. What are the forces acting on the car? Weight. All right. else?
It's frictionless, right? You said it's frictionless?
I did.
How's the car moving if there's no friction for the tires?
It came into existence already moving. If you really need something, then it enters the track. There's friction until it gets to the bank. All right, so direction of acceleration. Indeed, the acceleration is in that direction. So therefore, what do we need to, our coordinate system? What's our coordinate axes? Stone did it last time, don't expect him to do it this time. What coordinate system should we pick?
Up is positive and right is positive.
All right. And for those who are unsure, one of them probably should be in the direction of acceleration, and the other one should be perpendicular to that. All right, decomposition. Do we need to break either of these vectors up?
Normal force.
Yeah. So in terms of angle, I'm giving this angle theta here. So the question is this angle theta, or is this the complement of theta? Well, let's work our way through that. I've got my ramp here at an angle theta. My normal force is perpendicular to that. And I'm trying to figure out this angle here. Well, if that's theta,
It's the complement.
why is it the complement?
This is just where you're showing that's where theta is under it.
Yeah, that's theta there, therefore this must be what I'm going to label as theta prime. So if I'm looking at y here, I know theta is up there, theta prime is down here. So I break y up, I got weight acting down, y break going to the right and going up. This dramatic pause is for someone to break it up for me.
What was the question again?
We're breaking normal force up. I know there's a sine and cosine in there somewhere.
Oh, sine is going up, cosine is to the right.
Sine and cosine of
Yeah.
theta prime is the one that's here. So this is y times the cosine of theta prime, or y times the sine of theta. Depends on how you want to work that. And this is the other one, y sine of theta prime, or y cosine of theta. May as well just stick with theta. That one and that one. So we have now simplified, I got weight acting down. I have y sine of theta acting into the ramp, or not into the ramp, parallel to the Earth, or whatever planet it is, and then y cosine theta going up. All right, decomposition done. Now equations of motion. Go Go for it, Ryan.
Yeah. Y sine theta equals minus times acceleration.
Okay, one down. There's your I hat equation. There, just turn that on. All right, we got another equation to go.
Y cosine theta equals mass times 0, right?
Do. Technically, minus the weight is equal to mass times 0. All right, so there are the two equations. Now we do substitution. For what do we have an independent formula? And the formula for weight is,
mg.
all right, so this equation here becomes y cosine theta minus equals mg. Go ahead and bring it over. And then this equation we have one other independent formula that's appropriate for chapter 6.
B squared R.
Say it again?
B squared over R.
Over, okay. I missed it over the last time.
I didn't say it.
Okay.